So I've got all your submissions for homework 11. On Monday, you need to submit homework 12, which is related to water surface profiles, not including numerical integration stuff we're talking about today. It's mostly just conceptual ideas behind water surface profiles and application of the process equation. And remember that there is a recording you can watch to help you through the Darwin Designer portion of that assignment. That recording's posted on YouTube. I emailed you the link to that. So, any questions on these announcements? All right. Let's just review some of the information from last class period. Remember that if we want to know the slope of the water surface relative to the channel bottom, then we can find this dy dl. So dy dl is saying, how is the water surface depth changing in the direction of flow? Is it getting deeper? Is it getting shallower? And it takes into account the slope of the energy grade line, S sub f, and the channel bed slope, S naught. And what we talked about in the last class was that there are these three zones that are delineated by the normal depth, Y naught, the critical depth, and then the actual flow depth that you have at any certain location is going to go in one of these three zones. And what type of water surface profile you have is first determined by the slope. The slope being either adverse, meaning uphill, critical, meaning that it will cause critical flow, or more commonly mild, meaning that the slope does not support supercritical flow. In other words, a mild slope would support subcritical flow, or steep. So shown here are the M profiles, and when the water depth is above both the normal depth and the critical depth, that's when you have an M1 profile. And what this diagram shows is that an M1 profile in the direction of flow, the depth is increasing. In an M2 profile, mild slope, but the water depth is in between the normal depth and the critical depth. So water depth is decreasing. And with an M3 profile, that means that it's a subcritical slope, but that for some reason the water is supercritical. You can see that the actual flow depth is going to be below the critical depth and the normal depth. These images are taken from a variety of different texts, and I've taught hydraulic engineering out of 3 or 4 different books since I've been teaching college, and I put in all the different representations of water surface profiles because sometimes one different kind of drawing will appeal to a student, whereas the rest of them maybe didn't clarify the issue. And so we're going to go through a couple of different versions of these same things, just so hopefully it'll start to make sense, if it doesn't already, what these profiles mean, what causes them, and how to diagnose the flow regime, both in terms of whether it's supercritical or subcritical, but then also which of the 3 zones the water depth is in. So you can see the S profile, meaning steep slope, will support the supercritical flow, so that if the water depth is in zone 3, maybe coming out of an underflow gate, for example, then the water depth increases until it reaches the normal depth. This normal depth represents what the water conditions will be, what the water depth will be at under steady flow, steady uniform flow. So it will come back up into equilibrium and match that normal depth and then stay there. S2 profile, the depth is decreasing until it gets to that equilibrium of where it should be, the normal depth, once it's finally reestablished itself. An S1 profile, though, would be caused by some sort of an obstruction downstream that's causing cooling. A critical profile, prefixed with C, can only have a zone 1 and a zone 3. There's no zone 2. So why do you think that is? Look at the drawing that's just come on screen. You see that there's a C1 and a C3, but no C2. Josh, do you know why that is? Why there's no zone 2 on that drawing? Yeah?
Is it because the slope is the critical slope?
The slope is the critical slope, and so
there's no normal depth is the critical depth?
Normal depth and critical depth are on top of each other. Right. That's not shown very well in this drawing. They should have said y naught is equal to yc, because the normal depth and the critical depth are on top of each other. And so zone 2 is usually the area between those two places. And in this case, they're on top of each other. So zone 2 is infinitesimally small. The same thing, well, a similar issue is present on a horizontal slope. If the slope is horizontal, there's not going to be a normal depth. Normal depth is not defined unless you have some sort of a channel slope. So there's a critical depth, but there's no normal depth. And so there's no y sub n boundary to differentiate zone 2 from zone 1. So that's why there's no zone 1 in a horizontal slope, because there's no normal depth. And in an adverse slope, there's also no normal depth. There's no ordinary normal depth that water will flow uphill at. It only flows uphill when conditions are non-uniform, when it has a lot of velocity and it's slowing down as it goes uphill. But there's no uniform steady depth for an adverse slope. So that's why there's no A1 profile. You can't have an A1 because there's no normal depth. If the water depth is getting deeper uphill, that's an A3. If it's getting shallower in the direction of flow, that's an A2. There's no A1. Okay, so that's one version of looking at these water surface profiles. Here's another, and I like these water surface profile drawings because it shows what causes them. And you can use the water surface profile to know what sort of an obstruction or what sort of a feature downstream or upstream is causing the non-uniform flow that's being analyzed. And so in the case of that M1 profile, what it's showing is that maybe that is a downstream weir in a spillway in this example. So a downstream obstruction is what causes the water to go from its original normal depth, and the depth is increasing. So that illustrates the M1 profile. It shows that an M2 profile would be a mild slope that's decreasing as water flows over an edge. So if you're canoeing or on the river in a boat and you're looking down at the water and saying, oh, that's an M2 profile. We got to paddle faster because there's a waterfall downstream. So it's useful information for your safety. There's M2 profile. You know that there's a cliff on the downstream. M3 coming out of a hydraulic jump, or upstream of a hydraulic jump, coming from underneath of an underflow gate. There's the M3 profile. It's a mild slope, it's supercritical conditions, it's getting deeper in the direction of flow. So here are some of the causes of S profile types. The S1 is shown in all three cases being downstream of a hydraulic jump. That's the only reason why water would be above both the normal depth and the critical depth with a steep slope. Was if it's jumped because of pooling, an obstruction downstream that's forcing pooling. So ordinarily, in a steep slope, the water wouldn't ever be above the normal depth, the critical depth, but because of the spillway or a step up or a gate that's closed, that's forcing the water to be greater than both the normal and critical depth, and so that it has to jump up to meet that increased depth. So these are showing some of the instances where you maybe see an A2 profile or an A3 profile for an adverse, meaning an uphill slope, or if the slope is critical, how you could see a C1 or a C2, but again, there's no C3 profile because there's no boundary between the critical and the normal depth when the slope itself is critical. Finally, this is the third way to illustrate these different water surface profiles. Here, it's identifying what the dy dx will be, meaning that it's getting deeper or shallower in the direction of flow. So here, it's clearly showing that in a mild slope, normal is above critical. In a steep slope, normal is below critical. And then this thick black line is illustrating the depth at any particular location. So we're going to be comparing three depths: the flow depth, normal depth being what it would be if conditions were uniform, and then the critical depth, meaning the depth required to have the Froude number equal to 1. So I urge you to look through the book and let these water surface profiles sink in. And I earlier suggested maybe even going so far as to prepare flashcards so that you could drill yourself on what these different slope profiles are, because you may face a quiz or an exam where you're asked to classify the water surface profile type. Also, in the earlier example from last class's lecture, I introduced the equation from Mannings with a very wide channel. And I wanted to put it on the screen here so it's included in your notes, and so that you could put a little asterisk off to the side that this should only be applied when the width is more than 20 times the depth. So this is the case where the edge effects of the wetted perimeter, so those two sides of the wetted perimeter, is so small relative to the width b that they can be neglected. So don't put that on your equation sheet and think that it always applies. Only use that for what's been described as a very wide channel. All right, well, we're going to work an example, and the earlier class we used the tablet PCs, and I'm glad that we did, because I think everyone was getting rusty. Well, has gotten rusty on using Excel to solve the Mannings equation. And so if this class is like the last one, we need practice punching equations into Excel. So go ahead and grab a computer. What we're going to try and do is diagnose the water surface profile. So we'll do that by finding the normal depth using Excel. The critical depth we can just do on paper. And then once you have the three depths classified, you'll know y, y sub c, and y normal. Okay, y is given in the problem statement. It says that at a certain spot, the depth is 3.2 meters. Y sub c, remember, is flow per unit width squared divided by g to the 1/3 power. And I hope you have that memorized by now. You've used it enough times that that should be memorized. I'm not saying that it's required for you to memorize it. I'm just saying that if it hasn't been memorized, then that should be a warning sign. All right, the last thing, to find the normal depth, we're going to use Manning's equation. And of course, Manning's equation is Q is a to the 5/3 power divided by n times p to the 2/3 power slope to the 1/2. So what we're going to do, you using Microsoft Excel, is type in all of the variables, n, slope, q, y, and you know that the flow rate should be 31 based on what's given in the problem statement. So you'll put in the known value of n, 0.033. You'll put in the known slope that's provided, 0.001. And we're going to have to start off by just guessing some normal depth. Maybe the normal depth is 2 meters as a guess. And then you're going to have q as a function. So you'll type in the equation, the Manning's equation, in terms of this y, and then of course you'll be able to use goal-seek to change lots of different values of y, ultimately find out what is the flow rate. Does it match the flow rate, your goal of 31? Okay, so do that, and then we will pick back up and find the water surface flow.
Is that P for wetted perimeter?
Yeah, wetted perimeter. You don't necessarily have to have it. You could have just written the Mannings equation in terms of y and b. You could have built area and wetted perimeter into the Mannings equation, but it's a little bit simpler to have it outside of the equation and then just reference it as a quantity by itself. So where we're interested, the depth is told in the problem statement to be 3.2 meters. And we know from our Excel calculation that the normal depth is 2.717. And the critical depth is going to be flow per unit width, so 31 cubic meters per second divided by the 8.5 meter wide channel squared divided by 9.81 meters per second squared to the 1/3 power. And so y sub c is 1.107 meters. Okay, so let's draw a diagram of what this looks like. We've got some critical depth. Y sub c is 1.107. Y sub n is 2.717. And then our actual depth, y, at this point, y is 3.2 meters. And so that's how deep it is there. So what kind of a water surface profile do we have? Is it a mild or a steep slope, first of all? Mild. It's mild because the normal depth is greater than the critical depth. So that tells us it's an M. And then we delineate the 3 different zones, and where is the water depth in? Zone 1, 2, or 3? It's in zone 1, that's right. So this is an M1 profile, which means that in the direction of flow, it'll be getting deeper downstream. Deeper downstream. And let's test that out. So we should expect dy dx to be positive. dy dx should be positive, is what we expect. And so we're going to do that. First of all, by finding the slope of the energy grade line. Here in this next phase, we rearrange Manning's equation to find the slope of the energy grade line. We can write that as S sub f is n times q, p to the 2/3, a to the 5/3. So 0.033 is the end value. Flow rate 31 cubic meters per second. The wetted perimeter is 8.5 meters plus 2 times the 3.2 meter depth. And that wetted perimeter is to the 2/3 power. And the area is 8.5 meters times 3.2 meters to the 5/3 power. And so when we find the slope of the energy grade line, S sub f is going to be 0.000634. Slope of the EGL. That's that imaginary line above the water surface that takes into account the depth and also the velocity. Since we know S, we're going to be able to find S naught minus S of F. Let's find the Proud number squared. So FR squared, the formula for that is Q squared times T divided by GA cubed. 31 cubic meters per second times the top width of 8.5 meters. And that 31 cubic meters per second is squared. G 9.81 meters per second squared. And the area is 3.2 meters by 8.5 meters. That to the cubed. So the Proud number squared is 0.04138. So we're going to calculate dy dx with all the information we've got so far. Dy dx is S naught minus S of F 1 minus the Proud number squared. Okay. So the S naught, that's the slope of the channel that's given as 0.001 minus the slope of the energy grade line, 0.000634 divided by 1 minus the Proud number squared, 0.04138. Dy dx is the slope of the water surface relative to the channel bottom is 0.000382. Okay, so that's a positive quantity, which means it's going to be getting deeper downstream. And what we would call this, in other words, we'd say that this is the slope of the water surface relative to the channel bottom at the point where y equals 3.2 meters. Because remember that the water surface slope is constantly changing. Just to exaggerate what this channel looks like, consider that we have some channel bottom and a water surface that's curving. So that it's just at this point where we know that the depth is equal to 3.2 meters. That is the water surface slope. The slope of the water surface right there is what we've just classified. And we've classified it dy dx. That's relative to how steep the channel slope is. And so it's going to be either getting shallower or deeper relative to the channel bottom. That's what dy dx characterizes. So we found it's positive, and that coincides with what we should see on a mild slope. Here on the diagram it says that for an M1 profile, we should have a positive dy dx, and we did. Any questions about this example? In light gray, it asks the question, what if the depth of flow had been 2 meters? What would be the water surface profile type there? It's still going to be an M because the critical depth is less than the normal depth. But if y was 2, it would be an M what? M2, right, because it would be, if the water depth was 2, then that would put it in zone 2 here, between the critical depth and the normal depth. We're going to change gears a little bit now and talk about the physical measurement of river gauges, of river depth with a gauge. The next 3 class lectures are going to be devoted to talking about how we can find what the depth is upstream or downstream of a point where the water depth is known. And so this illustration is showing how we know what the depth is at a certain point in the river. If there's a river channel and there are these water intake pipes that connect the river channel to a static well, where it's going to be avoiding any sort of the influence of waves here in the static well or wind. And it's only the water level inside of the static well is only going to rise or fall to the elevation of the water surface itself. And then above that water surface is going to be some sort of an instrument that's recording the water depth, either electronically by sending an ultrasonic pulse down to the water surface, or it could be a float system that's connected to a line or a chain, and the distance of the line or chain relative to the recorder height is known and measured, and then sent by satellite to a consolidated data recording and reporting site. And that's what this USGS website is. This is a location where they're measuring the water depth for the Ohio River in Huntington. So you notice here on this page it's mentioning the latitude and longitude of the gauging station, the area that's upstream. 55,000 square miles is draining into the Ohio River at Huntington. So that's the upstream watershed. It tells you a little bit about how long they've had that data measuring station there. One thing that's kind of interesting is that it mentions that discharge is regulated by the locks, dams, and reservoirs upstream. And so the water surface is in some ways moderated by the Army Corps of Engineers and their ability to control how far open the locks and dams are. There's a dam about 15 miles upriver from Huntington is the Robert C. Byrd's locks and dams. You can see it just by driving on Route 2 up the river, and there's a big dam across the river, and they can basically control the water elevation to a certain extent, opening and closing that dam and regulate how much water goes through. And so this is showing over the last week approximately what the water elevations are at Huntington. You can see that the water levels were high because of some wet weather. Now they're declining. It was wet again last night, so I would imagine that over time that the water levels are probably going to come back up a little bit. So in general, when it's wet, they're higher. In some unregulated streams where they don't have a dam or a lock, then there's a lot more of a direct relationship between wet weather and the gauge height, which is what's shown here on the y-axis. So that's a little bit about how we know the water depth, and it's interesting that these gauges themselves sometimes become flooded, and as you go through the data, sometimes there will be these periods where it seems like the water level is really, really high, and then the data just stops, and that might be because the station itself is underwater. The first method we're going to go through that explains how to find the depth at some unknown spot is called the numerical integration method. And what it does is numerically integrates a curve. And you remember that in an earlier class, I told you that part of the difficulty in applying the process equation is that the water surface is a curve and not a straight line. And I'm showing it with this drawing that maybe if the water is going off of a cliff, that it's not a straight line between here and here. A straight line would be that, but the water surface is actually curved. And so if we were to try and approximate by finding the water surface slope here, what the depth would be, if we just sort of extrapolated where the water surface is going to be based on its curvature at a single point, we'd be too high. And so what the numerical integration method does is it says, well, let's try and approximate this curve as a line, but we're not going to make it a very, very long distance. If we just go over a short distance, then we'll probably get okay results. And to improve things even further, rather than extrapolating the water surface curve at the beginning or the end, let's do it at the midpoint. And so in this method, what we're going to be doing is we're going to have some unknown depth upstream and a known depth downstream. So the y1, if it's subcritical flow, we're going to be trying to predict the upstream depth based on a known depth downstream. And our process will be to apply at the midpoint these calculations that help us to predict what the new depth will be. So what's shown here on the screen is that we're going to be using the process equation, which consists of knowing the channel bed slope, the slope of the energy grade line, and the Froude number. We're going to compute the Froude number and their energy grade line slope with Manning's equation for the energy grade line slope. Froude number, this is the same equation we've seen before. We'll try and limit how far upstream we go, to between 30 and 150 meters as a maximum step. And we'll use smaller intervals when we know that the water depth is changing very rapidly. But we'll do these calculations at the midpoint because that's a way of our improving accuracy. We'll actually get into the procedure and the steps in our next class period, but what I'd like you to do is flip through that procedure and try and follow the example that's shown in the text just to fertilize your mind so that when we have the example and an in-class demonstration that you'll be ready to receive that information. Before I let you go, though, let's just take one final look at the announcements and remind ourselves that your next homework assignment is due on Monday, and that includes the Darwin Designer part of the cover sheet. If you have any problems or concerns with how to use Darwin Designer, you can check with Leland Johnson, who's our new resident expert on Darwin, or you can come to me and I'll stumble my way through Darwin. I think Vimal's pretty good at it right now too. So, anyways, that's due on Monday, and I will see you on Friday.